morning. Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Good morning. Good morning. All right, let me see if I can do this. All right, we're missing a board at the, oh, good morning. Oh, there's even, hello, Noelia. That's great. Hello, Jean-Pierre. Hello, Daniel. Hello, Alyssa. Hello, Amarani. Good morning, Asia. Good morning, Michelle. Hello, Ashley. I'm going through the chat and wait. Good morning, Luna. Hello, Chitlali. Good morning, Asia. Good morning, Melissa. Good morning, Jennifer. Good morning, Darina. Good morning. Did I say Sonia? Molly, I might have said twice. Sorry. Alyssa, good morning. Ronnie, I said, okay. Hello. Hello. It is great to see you guys. Okay. We don't, today may be funny. I'm actually amazed that this is working. I don't have, so my whole household just lost internet. I'm tethered, not to be, this is like, the typical sob story of the Zoom culture life. But yeah, it is one, good morning. Good morning, Daniel. Okay. Yes, in principle, my whole house does not have internet right now. And we just discovered this about 10 minutes ago. And my child is homesick from school. So we were, of course, thought we were going to send him to Internet University today, so to speak, or, and work on his Nintendo scholarship and all that. But so I'm currently, I actually was, this class may not, I don't know how far we're going to get in this class. Right now, we're tethering off a phone, which is fine. I am going to try to bring the board in. I don't quite want to do this without a board, but all of this may crash. So also my nerves might. So that's just a warning. Sorry. So we're not as up and running as we should be. But we physics wise, or so actually, I'm going to ask you to let me pause for 1 second here. Although, yes, I mean, a number of new homeworks came in and they went back and that was awesome. And I'm going to pause for a second and see if I can get this board working. Oh, and someone's here. Hold on a second. Okay. But yeah, I'm asking you to bear with me today because all of this is hanging on for today. Okay. Let's see if, thank you for your patience. We're going to try one more thing and see if this things work here. And if they don't, we'll all take this on faith. We're going to pretend this is Austin, Texas for a minute. We'll pretend. What's that governor's name? Oh, he's not even the governor. That's senator. What's that senator's name? The Cruz that everybody loves to hate. I feel like I got more information about him during that power outage than I did about the weather. Okay, I'm seeing if the board comes on. Oh, of course it won't because it won't unless it does. Whoa, we might have to assign. All right. Well, I'm gonna give up on this in a moment. I'm being a little desperate here, and oh, perhaps. Oh, perhaps. And while I'm stalling, I'm sure I've asked you this before, but if you've ever seen that YouTuber named Gus Johnson, who's like, oh, unable to connect. Come on, are you serious? Gus Johnson is very funny and satirical, and he makes fun of, he has this whole YouTube about professors, how to be a professor, and like he's making fun of them. and he does this whole thing about how professors are around technology and like trying to and it's very appropriate. It's very funny and very, oh, wait, maybe this is working. Maybe, oh, this might be actually working. Sorry, this is so interesting. Oh, do you guys see any evidence of, wow. Okay, so this is like, oh, all right, we're gonna try this. I understand that a bunch of elves carrying Legos are gonna be providing our internet connection today. And we have an oriented, oh, and we're gonna try horizontal. Whoa, we're gonna try horizontal just to, wow. Okay, this is, I don't mean today to be a psychedelic experience. I mean today to be, I've always felt, I've always felt a personality conflict about landscape versus portrait, and apparently it's being resolved right here. While literally my screen is saying your internet connection is unstable, but I think it means my personality. And it's, and we're here to talk about planet Earth and how we're hurtling through the universe at 65,000 miles an hour all the time. Right now, if you're feeling as sideways as I think you would be, because I'm feeling sideways, wow, okay, this is not gonna work. We may have to talk for a second. All right, we're gonna talk for a second. I apologize. I'm gonna try to fix this, but I don't even know why it would be that tethering off my phone would cause a rotation of my x-axis by 90 degrees. I'm not sure, but all right, I'll work on that in a second. Let's and then someone let in. All right, I do apologize for this. But since I was ranting last time anyway, I might as well finish the rant. The rant is about Galileo. Like what I was ranting about last time that is worth a little thought, and it maybe got across, and I want to throw it back to you guys and all that. But like Galileo looked at the sky through his telescope, realized he was about 4 to 10 times closer to the sky than any human being had ever been in the history of civilization before. Like, right? Like, I mean, he's not physically 10 times closer, but it is. If you're magnifying things by 4 to 10 times the amount, then it is as though you have, traveled 10 times closer to that object. I mean, that's the effect. So you're seeing things that have never been seen before, like literal lights popped into view for him. Let me back up and say that, the old science is about data. Any branch of science is about data. And the oldest living data set, arguably, that human beings have ever used for any purpose whatsoever. Like the oldest living, like think about what data has survived from what laboratories where, like what pieces of paper have survived from the earliest historic, like do we have numbers that, well, if you think about it, the oldest data set really in the world is the stars, right? Like everybody has been looking at the same sky. Anybody who's ever looked at the sky has looked at the same sky as everybody else for thousands and thousands of years. And it's totally mapped out and drawn out, and people know it, and people have figured out, the whole structure of the universe from carefully watching these patterns in the sky forever, like way before Galileo. Galileo, lives from 1582 to 1642. He's not the first person to look at the stars by any means, but he's now 10 times closer to them than anybody has ever been before. And he knows it, right? I mean, that is a crazy place to be. I mean, it is kind of like being an astronaut and landing on the moon in a way, just in terms of having a different perspective on the whole world. So he looks in the sky and dots start popping into view that have never been seen before, right? Like that's already interesting. Oh, and that's what I was gonna say, I'm sorry. So the number of stars in the sky that people have been seeing with their naked eye is approximately 1,500. Like on a clear night in the sky, if you're paying attention, there's between 1,000 and 2,000, so roughly 1,500 points of light that are, there and distinctly visible. Like if you pay enough attention, you get to know the patterns and everything, and you draw them. Like there's like 1,500 of them. Okay, Galileo sees 4 that come into view that no one's ever seen before. 4, like in a clump. So first of all, he knows, oh my God, I just discovered 4 stars that no one's ever seen before. That's pretty cool. Like I'm the first person in the world to know about these, not just 1, like that'd be cool enough, and not 2, but 4. Okay, that's a big leap forward. One guy seeing 4 stars that no one's ever seen before. But he starts paying attention to the 4 stars night after night and notices a number of really and he gets ready to name them after 4 princes who like he's hoping to get funding from. I mean, he starts being very politically wise about it. What he's actually going to do is dedicate this book, The Starry Messenger, that he's going to rush to print, the one with all of his drawings. He's going to dedicate that to these 4 princes and name the 4 stars after them, all in a very clever hope to get like major funding from them. But the 4 stars, he notices night after night a couple of interesting things. First of all, they're not. I don't know how far should I go into this? Well, he notices night after night that these 4 stars are very near what we know as the planet Jupiter, and what he knew as the planet Jupiter. And people did know about the planet Jupiter. People knew about the planet Venus. People knew about planet Mercury. People knew about planet Venus. People knew about planet Mars for thousands of years. But it's really important to understand why they called them planets. It's really important to understand what people knew about Mercury, Venus, Earth, Mars, and Jupiter, and Saturn, I'm sorry. About those 5 were called planets for the very simple and huge. Actually, does anybody know? Have I mentioned this in the room? Wait, maybe I should stop for a second. Have I mentioned, this is a real, I mean, I know I'm just talking, but this is like a very real thing. Have I mentioned, or does anybody in the room know why those 5 objects were identified as planets or called planets? Or put another way, does anybody in the room know what the word planet literally means in Greek? Possibly? I'm just a random question. I'm not expecting that you would. And maybe I'll even pause to fix the board while I ask. Because I know I should be writing this down. Well, I'll say here, and this is a very, like people knew about the planets. People for a long time, for thousands of years, they knew about Venus, and whatever name they called them in whatever culture. Lots of cultures knew there was something special about Mercury, Venus, Mars, Jupiter, and Saturn. And it's not that they look, so I'm going to spell this out for everybody, and I apologize that I can't be writing this right now. But it's not that they look any different from any of these other dots of light in the sky. I mean, yeah, Venus is pretty darn bright. It's super bright. That's true. But Mercury is not particularly bright. Mars is not particularly bright. There's tons of stars that are brighter than Mercury, Mars, even Saturn. There's tons of stars. Venus and Jupiter do happen to be pretty bright, but that's not what makes them particularly interesting or in a group or categorized as planets or anything like that. The reason the ancient Greeks called those 5 objects planets is the same reason they called 2 other objects in the whole sky planets, neither one of which was Earth. Planet simply means, and please do write this down, like this, it's all physics, even though I'm not writing it. Like planet means wanderer. And the interesting and the sole fact, the powerfully interesting fact about those 5 objects is that they wander through the sky, meaning, if you're trying to understand like motion, it all begins, like our whole concept of motion and all the laws of motion on Earth all first begin with our concept of motion in the heavenly bodies, in the skies, stars. So it's important to understand how they move. They are our original data set, like way before inclined planes or anything else. They're everybody's data set, like for everything. And what the stars do is like all 1,500 of them. Like if you look up at night, I mean, New York City, there's tons of light pollution. It's like hard to see a bunch of stars. But if you're anywhere in the world ever, and it's a clear night, winter or spring or summer, and you look up without even glasses or anything, you can basically see like 1,500 points of light in the sky. And the important thing to understand is that if you stood there in the sky, even for minutes, but certainly hours, you'd see that the whole sky rotates from east to west. All the stars rotate from east to west, like in the way that you think the sun does. Like you think the sun, I mean, I'm not saying you're wrong, but like to whatever extent you are used to or believe that the sun rises in the east every morning. Like if I'm, so if I'm standing facing south here, like over there, my left hand, and then as the day goes on, the sun goes higher and higher in the sky, like toward the west, toward the south, and then at the end of the day it comes down, down in the west, down, down in the west. So it goes from east to west every day, the sun. And I'm not trying to condescend to anybody by saying this. I'm trying to ground everything in like something we know. This is like where we get all our knowledge of motion. Like the first thing that people kind of notice is that the sun goes from east to west every day. What I'm trying to tell you right now, that's a little bit harder to notice, like you could go through your life without realizing, is that it's not just the sun that does that. It's the whole sky every day, all the time, is just continuously, smoothly going from east to west. Like it's not just the sun, it's the whole sky, meaning that if you looked at the stars at night, the whole group of them, this is what people mean by the canopy of the star. And again, this is like really obvious to some of you, maybe because you already know it. And to others of you, even as I'm saying it, it maybe sounds really obvious, even if you never thought it. And others of you, it might even, like, it was weird to me when I first heard this, but hopefully you could at least picture. I am saying the whole sky moves together all as one. So it's like you put a big black sheet over your heads and you put lots of dots. I mean, like, like white dots on the sheet. And every day, all the time, the whole sheet is just moving past us, right? I mean, like the white lights in the train example, excuse me. and all it takes is to be out at night, all night, to notice that this is happening. Like it's just as easy to notice as the sun, as noticing the sun. And you don't blind yourself looking at the stars, but you have to be out at night to notice it. Here's the catch, though. Here's the thing. With 1,500 dots of light going across the sky every time, well, there's two big dots of light that aren't stuck to the whole canopy. We call them the sun and the moon, right? Like the sun is part of the canopy, but it drags a little bit. It doesn't stay with all the other stars. It drags behind so that it moves past the star. Like every day where the sun is relative to the stars is different because the sun is not fixed to the whole canopy. That might not surprise you. The sun seems so different after all. Like, why should it be stuck? Right. I wouldn't disagree with that. Same thing with the moon. The moon is not stuck. I mean, both the sun and the moon, you may or may not know, both the sun and the moon rise in the east every day, go up to the top and come down. I mean, every cycle, they both rise in the east and go down to the west, sometimes together, sometimes not together. Like sometimes the sun's doing it during the day and the moon is doing it during the night, but not always. It feels that way, but it's not always. But they're not in sync with each other, but they're both going east to west, just like the whole rest of the sky. Only now when I'm beginning to try to argue here, and I'm trying to sneak up in a way and say something, which is that picture, the whole sky goes like this, like this. The sun is part of it, but drags behind. The moon is part of it, but drags behind even more, so to speak, okay? But then there's these five dots that look indistinguishable from all the other 1,500. Like there's 5 dots that there's nothing special looking about them. You would just, if you ever, in other words, on any random night, if you just looked up and saw all the stars, the 5 that I'm talking about are just like there somewhere. They wouldn't pop out at you. They wouldn't like make themselves. They're not different color necessarily. Like they do have a little bit of color-ish. Like Mars is a little bit reddish. It's true, and Jupiter is a little bit orangish, yellowish. But that's also true of many stars. Have different. Like Sirius is bluish. Stars do have color tints. That doesn't make them like wildly, crazily special. These 5. Mercury, Venus, Mars, Jupiter, Saturn. The reason they get their own like special names or whatever, I mean, lots of stars have names, but the reason they is that they're not stuck to the canopy. That these 5 act like the sun and the moon. They're just 5 dots that do go across every day east to west, but at their own speeds, not just at their own speed as a group of 5, but each at their own speed. So in other words, in all of the 1,500 dots of light that go past us every single day, there seem to be a total of 7 that do their own thing. Again, I'm sorry I'm not writing this down. This is like real informational, honestly. I mean, to me, this is like the most interesting information in the world, actually. But this is like the birth of physics, so however you want to categorize it in your notes. But it's also like, and it's also ultimately going toward the definition of velocity. But what I'm saying is, just as a thing that people have understood for years, but only people that care, is that Oh, said someone here. Sorry. And I should be, for all I know, I've lost all of you. But every, on a daily cycle, whatever is clear in your minds, whatever any of you can picture about, like, yes, every day the sun rises in the east, goes to the west. And if you can picture that happens smoothly, like, I know you don't watch it with your eyes every day, but if you're sort of comfortable, and that means, by the way, I should say, if you're facing south, like if you could picture yourself facing south, like if you live in Manhattan, facing downtown or whatever, if you're facing south, what I'm saying is the sun rises in the left and it comes down in the right. Like, not to be weird, but just so you can orient yourself in the world. If you're facing south, and you do need to face south to see this happen, because we live in the north of the earth. So if you face south, right now, if it's in the morning, the sun is sort of over there somewhere in the high left hand part of your sky. And through the day, the sun's going like this down toward the right. What I'm arguing, Tim, but I want to make it clear, and it's not, you shouldn't be embarrassed if you didn't know this. And in fact, you really should ask yourself to what extent you might or might not have known this before. I'm saying the moon does the same thing. Whatever you believe about the sun, every day, smoothly, like not in jagged lines, but in as smooth a way as possible. So from east to south to west, the moon's doing the same thing every day, I'm telling you, and every night. Just it's doing it. It takes 24 hours, just like the sun does, and all the stars that you've ever heard of in the zodiac, like whatever your zodiac sign is, like if you're born in January and you're a Capricorn or whatever, that group of stars, Capricorn, it's doing it every day. Like I'm saying, always from east to west. And Mercury, Venus, Mars, Jupiter, Saturn, those five are also doing it every day and all sort of in the same region of the sky. But all the stars are together, all these dots are together, and 7 are apart. 1,500 dots of light. It's like the white lights on the subway, okay? Like through history, imagine you're paying attention at night, maybe just because it's beautiful, or because you're trying to figure out what the heck is, like, where do we live, what's going on in the world, and you're looking, and every night there's 1,500 dots that all move together past you at the same rate, same cycle, all predictable, all smooth, all the time. 1,500 of these dots, but then there's 7 that follow their own speed. Not only do they not follow all the rest, but they don't follow each other. 7 on their own path. Now, 2 of them look kind of weird, the sun and the moon. So we're like, all right, not that surprised. Somehow they're special. I guess they're closer to us or something. But the other 5, why are there 5 things that move differently from all the rest? Nobody knew forever. And they didn't even bother. They just called them wanderers. They wander. There's these 5 special things that somehow wander across the sky at the same in the same kind of motion as all the rest, but not at the same rate. In fact, of these 5, all right, so there's a total group of 7. Sun, the 7, and in fact, please write this down, since I am, like, just to ground this, I'm saying the original 7 planets, which actually literally is Greek for wanderer, the original 7 wandering objects that cause more sort of curiosity and mystery and intrigue and scientific probing in the history of the world than many other things I can think of. The 7 exceptions to the rule are the sun, the moon. These are the 7 original planets. Earth is not one of them. Earth is not originally called a planet. Pluto is not originally called a planet. Neither is Neptune nor Uranus, because no one's ever heard of them, because no one can see them with their naked eye. They only get discovered way later once we have really powerful telescopes. But the 7 original planets are Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn. And one way of remembering that group, and that's, by the way, all the mysticism surrounding the number 7, lucky number 7, God rested on the 7th day, all the stuff. And I'm not saying I don't believe a lot of that stuff, but all the associations with 7 come from the fact that 7 has been known for thousands and thousands of years to be the number of heavenly exceptions to the heavenly rule. There are 7 things in the sky that don't move like all the rest. We named the 7 days of the week after these 7 objects, right? Especially if you know those days of the week in Spanish or in French right? Like lunes, martes, miércoles, jueves, viernes. Like think about it. It's totally the 7 planets, including the sun and the moon, not including Earth. Earth was not considered a planet because a planet is a thing in the sky that moves in an unusual way. There are 7 things in the sky that move in an unusual way, and I just like named them. Now, why am I off on this big tangent? But remember, this is our concept of motion, like going into Galileo, like everything in the heavens moves in infinite circles. Everything on Earth moves in finite straight lines, and it's 2 completely different like worlds of motion. But Galileo is looking up there, and Galileo notices these 4 stars that have never been seen before, and they're very near the wanderer Jupiter. Okay, but then he notices, but watching them night after night. I wish I'm going to try one more time with the board in a second. Watching night after night, he notices a couple of really strange things about these four stars. They're near Jupiter, but like Jupiter, they're not staying fixed to the heavenly canopy. It's 4 objects that are also not moving like all the rest. So the number, remember, there's 1,500 objects that are all 1,500 points of light that are all moving together all the time, past us. And again, like the white lights in the train, they're moving past us all the time. So you could say to yourself, these things are moving past me. I'm obviously standing still, but it might flit through your brain once in a while, depending on who you are or where in history you live or what. It might flit through your brain like, well, that's odd. Like, why are there 1,500 things all attached in the universe, all moving together all the time? Like, that seems like sort of unlikely or complicated. Maybe is it possible that they are one thing, that they're all stuck and I'm moving past them? Like, it's like with the white lights on the subway, you see a bunch of things going past you. Either they're going past you or possibly you're going past it. It may occur to you to entertain both possibilities. You might even be smart enough to be confused, if you know what I'm saying. Like, it might even occur to you, like, 1,500 things moving together all the time. Maybe I'm the one moving, but that's weird because your feet aren't doing anything weird, right? And then on top of that, to complicate things further, there were these 7 things that always move differently from all 1,500. But now Galileo's looking through his telescope and he sees 4 more wanderers, right? What I'm trying to say with all my other background, I'm saying now it's weird enough that he just discovered 4 stars that no one, I mean, it's not weird. He's got a telescope. That's what he's trying to do, but it's interesting. But now when he looks at them closely, he realizes they're not stars. They're wanderers. They're not staying fixed to the canopy. They're moving through it the way Jupiter moves through it. So there's only been 7 for all of history. There's only been like literally the week surrounds these 7 objects, and Galileo just found 4 more in one swoop. Like, that almost doubles the list, right? That's kind of crazy, and it's particularly crazy when many of you may know where this is going. And all right, I'm just going to try drawing now. I'm going to see if I can just do this. He sees like this. Okay, I guess I'm drawing. All right. Okay, this doesn't look very elaborate. You can look up these images on the web, but in his sketchbook, that big circle is supposed to be Jupiter as seen through his telescope. Okay, it's still just a circle. I mean, it's not like, and remember, and no one's saying anything yet about, like, when they talk about planets, they're not talking about like places where space aliens, live, or where there might be canals and water. That is not what planet just means. Wandering object, or wandering point of light. So Galileo is noticing these the 4 little dots are these new objects that he notices near in Jupiter. But this is all with a background of stars everywhere. So Jupiter is moving through the background of stars night after night, as it is expected to, because that's why we call it a wanderer. But so are these new 4 stars that pop into view. And not only are they moving through, but what they seem to be doing, as you can sort of tell by the picture, is they always seem to be near Jupiter. They always seem to be sort of in a line near Jupiter. You see where this is going. And they move around, but they move around sort of within, like they move around relative to the canopy of the stars, but they seem to stay fixed to Jupiter, and they seem to dance like back and forth. Like first stage, like night 1, there's 3 stars on the right side and 1 star on the left side, and then night 2, there's 2 stars on the right side and 2 stars on the left, and then night three, there's only 3 stars. One of them you can't even see at all because it's behind Jupiter. Because does anybody see where this is going? Oh, I'm looking in the chat. Sorry, I'm totally losing. Maybe someone sees where this is going in the chat. Yeah. Oh, good. Oh, sorry, I totally missed that. Someone had said, "Oh, that's awesome." Someone totally did get the definition of planet, and that person should definitely put this in their game points. I'm sorry. I'm really in outer space myself today, but yes, that's awesome. Right, planet does mean wander. So these things, does anybody get what I'm saying here? What these things are that Galileo is tracking or discovering for the first time, or like why there's 4 of them. There's 4 of them, but sometimes even only 3 are visible because one of them is like behind Jupiter or in front of it. And they keep moving around Jupiter, but in a line like this, while Jupiter moves through the canopy of stars. Anybody guess what where I'm going with this? Or should I just say it? Well, what these things are, or what we now call, what Galileo decided, and we still agree today, is these are moons of Jupiter. He found wanderers of wanderers. He found objects wandering around an object, a wanderer. Like, and these are the 4. It turns out that Jupiter has like 50 going around, and Saturn has a bunch too. Like, it turns out planets have moons. Nobody knew that to this point. He saw a world within a world. Like, remember, we're still the center of the world. We're looking at these things out in space, these dots of light, but then he sees closer dots of light. And this is all like, and the only, I think partly what I'm trying to emphasize about this, why I care about this so much, I know it's abstract and historical and stuff like that, but part of what blows my mind is like all we can know about these, all there is in this data set, is literally dark space and white dots. I mean, it's like the ultimate binary field, right? I mean, it's zeros and ones. It's just black or white. But people have been looking at this painting for thousands of years, and the painting always moves, but in a cycle. Like, it moves in a pattern. So it's always to say it's a movie. I mean, it's not a painting, it's a movie, the sky. But all it is a scatter plot that everybody's been looking at for thousands of years, and drawing and writing that and getting the patterns, and people knew the patterns. And in other words, if 4 new dots pop up, you know that they're new. What he's seeing here is, oh my God, there's a pattern within the pattern. There are dots that follow dots. Like, until this time, we only knew of 7 dots that moved in their own special way at all. Now we're fine. Now he sees like another layer, that 4 dots are going around one of the 7 dots that travels through the 1,500 dots. And it's called a moon of Jupiter. I mean, or he calls it a satellite of Jupiter. He names the 4 Jupiter. Well, he names them Io, after Greek goddesses, Ganymede, Callisto, and Europa. Now, and these things, okay, Jupiter, it turns out, is huge, and these things are huge. Like Europa, the moon of Jupiter, one of these ones that Galileo discovered. At this point, I mean, it's more likely that there's that thing is so huge and likely has water. There's more of a likelihood that the atmosphere of Europa is similar to the atmosphere of Earth, and that the living conditions are more similar on Europa than possibly any other place in the solar system. I mean, but to him and to everybody, it's a dot of light at this point. It's just a dot of light that no one's ever seen before. And he goes, oh my God, there's a universe within the universe. There's a world going around a world within this world. That's crazy town. And as long as I'm talking about it, as long as this is what I'm talking about today, it goes one, and I guess I'm using the board, he goes one step further. So Okay, very quickly. So Galileo saw a bunch of things with the telescope. No, in other words, Galileo got new information. Galileo standing there like, we need more information. We need more information about, because the sky's been going past the Earth forever. Everybody's seen it go forever. Everybody's been saying the sky is going past the Earth is standing still forever. And it's not crazy to say that because, like, we're standing still, we feel stable. Why wouldn't we say that? But you, like many of you, with the train of thought thing, like if you're asked directly, am I moving or not? And again, most people did not ask themselves this directly about Earth. I mean, only certain people asked themselves, only people that were paying attention to a certain kind of question. But if you were to ask yourself, wait, do I actually know whether I'm sitting still or I'm moving, like in the train of thought thing? Many of you rightfully then say, like, I think I need more information now that I think about this, because, like, there's not a lot of evidence to suggest I'm moving, but there's also not evidence to suggest I'm not moving. I need more information. Well, Galileo is getting more information. Some of the more information he gets, I just described, like he gets, oh my God, Jupiter has moons going around it. That is crazy information. It doesn't prove anything except that whatever we thought we knew about the universe before clearly isn't the whole package. Like, it proves that we don't know what we don't know, but it doesn't prove anything specific beyond that. But then he also, a couple other things that are historically important. I mean, not so much in this class, but he sees that the sun is not perfect. Like, he sees sunspots. He also looks at the sun a lot and draws it a lot, and it's pretty wild. And then he eventually goes blind from doing that. But one of the first revelations is he sees the sun's not perfect. It's not a perfect heavenly sphere. It has color discolorations and things that we now associate with magnetic fields. But it's just, up until that point, everything in the heavens seemed to be perfect circles, just infinitely maintaining radius from a center point, etc. And then he saw imperfection there, so that was alarming or concerning. Also, similar with the moon, he could see the shadows in craters a lot more closely than anybody had before, and saw that the moon actually had a three-dimensional surface rather than a two-dimensional surface, which also suggested some kind of new way of looking at the universe. But the thing I want to really emphasize here is number 4. It sounds abstract, or it sounds weird, but this is my favorite one. Since we draw this stuff at the beginning of class every day, with the phases of the moon and all that. Well, here's what happens with Venus. Remember, Venus, again, is a dot in the sky that everybody's been calling planet for thousands of years because it's not fixed to the canopy of stars. Oh, but by the way, I need to make clear, no one knew why that was. I mean, that's why these 7 heavenly objects were like the subject of so much drawing and thought and investigation and scrutiny. Like, there's no explanation there, but Venus just was one of the objects that seemed to travel its own way compared to all the rest of the stars. And so Galileo looked at Venus night after night through his telescope, and with his telescope he's 10 times closer to Venus. What could he see about Venus that wasn't, now unbeknownst to, well, what could he see about Venus? You see where I'm going with this? With Venus, if he looked really closely and started drawing it night after night, after a while, not right away, but after a while, he was like, oh my God, that's not even a perfect circle. Like, not just an imperfect circle, not like a circle with bumps on it, but wait, that's a half circle. Venus is a half circle. Wait, no, it's a crescent. Wait, it's a crescent the other way. Wait, Venus is doing that crazy thing that the moon does. He noticed, because only he could see it closely enough to see that. Like, not because anybody else is an idiot or anything, but like, it just wasn't there to be seen. But now he sees that Venus is actually changing shape throughout throughout days, the way our moon does. Nothing else in the sky does that besides our moon. Why does? And we were used to the fact that our moon did that. We had an explanation for that for thousands of years. An explanation, I might add, that was totally correct, or at least that we still believe to this day, even though it was an explanation that was come up with, by a bunch of people who absolutely believed that the Earth was sitting still at the center of the universe. Like, why does the moon, okay, I'm going to pause for a second. Why does our moon do that? Like, I mean, why does it look like half of it's disappearing half of the time? It doesn't. Presumably, it doesn't really actually disappear. Presumably, it's not like actually losing matter. So why does our moon go through phases? Does anybody? Oh, and someone just came in. Any thoughts? Or should I repeat the question? And this is definitely a class participation thing, blah, blah, blah. Maybe okay. And also it's partly because I know I know we have to get back to the homework too, but what, has anybody, did you understand or could anybody, do you understand the question I'm asking is, oh, wait, oh, yeah, oh, no problem. No problem. I'm looking at the chat. Oh, that's pretty interesting. I'm looking, okay, so I'm getting a couple of things in the private chat. Pretty interesting things in the private chat. And what? Yes. Okay. Yes. And I'm just going to respond. Yes, that's good. All right. And no worries. And I'm also getting things in the private chat about other people having tech problems too. Look, I know. Yeah, I am just one big tech problem today. Yes, the shadow. The thing with the moon, just to make clear, and again, this is all in a way like basic astronomy, but this is where physics comes from. The thing with the moon is that it's going around us while either the sun goes around us or we go around the sun, whichever way you want to say it. But the fact is, right, sometimes the moon is directly in between. Wait, let me back up. The fundamental point that's obvious once it's said, but it's not obvious until it's said, is that the sun makes its own light. The moon does not, right? Anything we see of the moon is light bouncing off the moon, is light that came from the sun and then bounces off the moon to us. This is a very important distinction, right? Like the sun is like a light. It's like a light bulb. Like when you see a light on in your ceiling and you can see that the light is on, that's like staring at the sun. But when you see a doorknob in your room, once you turn your light on and you can see a doorknob, it's not because the doorknob makes its own light. It's just because light from the light fixture is coming to the doorknob, bounces off the doorknob, and goes to your eye, right? Now, either way, the light has to come to your eye. But from the sun, the light comes directly to your eye. From the moon, the light has to get first from the sun to the moon, then to your eye to see it, right? So you need both objects involved to see the moon. And the orientation that they're in totally affects how much of the moon would be illuminated. Like if the sun and the moon and you are in right angles, then you'd only see half the moon. So the moon does not make its own light. And we know that because the moon changes shape once a month, and we assume it's not actually changing its shape. It's just the way we see it, that it can fall into shadow. And put one other way, and I think it was Daniel or someone put, oh, I'm going to look in the chat. I'm sorry, but someone put in the, oh, yeah. Okay. Oh, right. Very good. So again, so some people are in the public chat and some people in the private chat, but yes. And it was Daniel. Um, right. The moon goes around and around the earth. It's going around the earth. So where it is, what its position is affects how we see it. Yes. But absolutely, this all has to do with reflection. It is like a reflection. It is a reflection. And shadows are relevant here. Just it's like this is related to reflections and shadows in the same way that any normal, regular, everyday object that you ever see. Like this is what didn't occur to me until it did at some point. Like any normal object in the room that you're looking at right now, like not your computer screen, because that's different, but anything in the room that you like a soda can or a coffee cup or a book, all of those objects, you're only seeing them, right? Because light is reflecting off them to your eye. Like for your eye to see something, and I mean this like seriously, I don't mean this as a condescending, like all of this stuff has to be spelled out as far as I'm concerned. It certainly does in my brain. Light has to get to your eye from a thing in order to see that thing. But most things do not make their own light, right? So we have light fixtures in rooms or whatever. We have light sources that make what we call ambient light. Like the light sources send light everywhere in the room, like in all directions, and the light is bouncing off everything in the room. And so in order to see an object in a room, you need light to make a straight line from the light source to that thing, and then from that thing to your eye. So it's true that like everything is reflecting it. Not everything, it's confusing because not everything looks like a mirror. Like you don't always see yourself. Like a mirror is like another level of reflection, but everything is reflecting light from a source to your eye. That's what the moon is doing, but that's what vis-a-vis the sun. But so even though the sun and the moon are always moving past us, right? Like the sun always looks like the sun. It doesn't matter where it is because the light comes directly from the sun to our eyes, and that from all of the sun, and nothing can block that. I mean, things can block it, but the moon, the light has to get from the sun first to the moon, then to our eye. So that means the moon is so yeah, like when the sun is rising and the moon is at the top of the sky, like when they're forming right angles, that is a half moon. If you, or a better example, if the sun is setting in the west and the moon is in the top of the sky, like you see the moon at the top of the sky as the sky is, it will be the right side of it that's illuminated. The sun is down here to the right. The moon will be up at the top of the sky. That's like a first quarter moon, a waxing half moon, when it looks like a D. The side of the moon that's pointing to the sun down over there in the west, that side is illuminated, not the other side. Okay, but it turns out Venus does that. Venus does that. Nobody knew that because we're not close enough to see that it does that. But if we're close enough, we do see, and Galileo did. So Galileo was like, OMG, like Venus doesn't make its own light. He never knew that before. Nobody knew that before. In fact, it's a crazy thing to know because Venus actually is super bright. It's actually brighter by just coincidence. Well, because as it turns out, it's so close to us. Venus is brighter than any star in the sky. Like again, Mars is not, like Mercury is not, like planets don't have to be, but Venus happens to be super bright. People used to call it the morning star. They also used to call it the evening star. Venus is bright, and yet it doesn't make its own light. It's like apparently like some kind of rock up there, like the moon. That's weird. And there's a world inside of a world going around Jupiter. That's weird. None of these things by themselves prove anything, but they are definitely bringing a lot more information into the game for Galileo. And they suggest very strongly, or they suggest with more strength than ever before, the possibility that like maybe we're not the center, right? I mean, if there's worlds within worlds, oh, well, right. I mean, if there's worlds within worlds, and it's possible for rocky, non-producing, imperfect objects to be out there in space, acting like points of heavenly light, then isn't it possible for this rock to be a rock in space, right? It doesn't prove anything. It just opens up a possibility, or it breaks down. It gives further and further reason not to. But okay, so wait, what time is it? I probably lost the whole. Sorry, hold on one second. Okay. So now I'm going to try to bring this back. I know this is like all. To try to bring this full circle, I'm saying, right, if you're Eddie, if you look down, there is no evidence to suggest, and there's no rational, like logical reason to suggest saying that your floor is moving, right? It's not dumb to think that the earth is not moving. It's almost dumb to think that it is. I mean, or certainly this, it's definitely dumb to believe that the earth is moving just because somebody tells us, right? That is just as dumb as believing that the earth is not moving just because somebody tells us, right? Uh, and Galileo is looking up and gathering more and more reasons to be suspicious as to whether the ground below is actually sitting still or not. But he's no dummy. He knows that even if he starts saying to people, I think Copernicus, this guy Copernicus from like 50 years ago, might have been onto something with a moving Earth idea here. Even if he starts saying this to people, they're going to be very right to say, wait, what? I mean, look down. Like, fine, you're seeing interesting things looking up, but what about looking down? I mean, get a hold of yourself. And here's the thing that one of the many things that's weird is I can now, with the benefit of hindsight with you guys, I could say, Galileo had this telescope, so he had this new data. So now he can knock people out with that, and he's ahead of his time, and he was ahead of his time. But put yourself in the situation like, and this is what's so funny about science too. Even if you're a reasoning person and you're even open-minded and you even want to hear what Galileo has to say, and you say to Galileo, like, dude, how fast you say this ground is moving below us? And now Galileo has to say, well, according to the calculations that would make this whole thing work and everything, if you do see where I'm going with this and you accept that the earth might be moving, it's about 65,000 miles an hour. Okay. You have to remember that when we say that the earth is moving, if you believe that the earth is moving, well, first of all, you believe that the earth is like rotating around its own axis at approximately 1,000 miles an hour, like almost like the speed of sound. And then the earth, while it's going like this is the modern view. I mean, if you watch like PBS shows or whatever, or even like Schoolhouse Rock, I mean, if you want to believe that you're standing on a thing that's always going through space, then you have to understand that it's going like this at 1,000 miles an hour, and it's going like this at like 65,000 miles an hour all the time. So someone comes over to Galileo's house and it's like, now, I'm not saying this literally happened like this, but you're saying the earth is moving? Galileo says, yeah, the earth is moving. You got to check this out. You got to see what I'm seeing up there. And the person says, and it's moving at 65,000 miles an hour. And Galileo says, yes. And you haven't had too much wine to drink here. Like you're really, yes, 65,000 miles an hour. So now, what's this evidence you've got from the heavens and from the sky that lead from the heavens that leads you to believe this? And Galileo says to you, yes, I've got evidence, reality, yo. Come over here and I'll show you. And he takes your face and shoves it into some wacko can that's like on a tilt, on a stand, and it's got some glass in it. And he shoves your face in this thing and then puts this tube at your eye. And then you're looking at like some glass in a tube and there's dots in the glass and they're kind of big. And God was like, see, Jupiter has moons. Like, what? Like, what? Do you see what I'm saying here for a second? Like, remember, we're calling this stuff data. We're calling it information because we have our instrumentation here in life at John Jay. I mean, even in a virus, we have our concept of what we believe and stuff like that, and like telescope, advanced equipment. And the more advanced it is, like the more we believe it in a way. But wait, but equipment starts as equipment, right? If you've never seen a telescope before and someone just invented it, and they're talking to you about reality and talking about skies, and they take a can and shove it in front of your eye. Like it might as well be a microscope for one thing, but they didn't have those either, right? And microscopes, you look at weird things down below, like from your fingernail, and people start telling you that like your skin is made up of cells or something, right? And you accept that. I'm not saying that's wrong, but I'm saying one way you look, someone shoves an eye in a, shoves your eye in a tube and says you've just gotten a glimpse into the micro universe of your own skin. And in another case, a person shoves your eye in a tube and points it this way and says you're looking at outer space or you're looking at the heavens. No, you're not. You're looking in a tube. You're looking at a piece of glass that, yes, pointed over there, but you don't know what's in that tube. You don't know if the guy just didn't make a kaleidoscope like thing like that, you can buy at a kid's fair, those. Like you can buy things at a kid's fair, which is a tube and has two things of glass in it, but has a whole bunch of like colored specky like sands and some in it, so that you put this thing in front of your eye and you go like this and you're seeing all kinds of cool colors and weird things. But that's because they're in the tube, not because they're like out there, because they're in the tube. And this guy's shoving your face in a tube and pointing over there and saying, now you've just glimpsed at the heavens. And I've just told you that the number of objects in the universe that are wandering through stars just doubled. And I'm telling you that there's worlds within worlds and that Venus is made of rock. And you just looked in a tube. Why would you call that data? You would say the man is either like up to some black magic, weirdo, sorcery, alchemy stuff, right? Which would be like the modern equivalent of someone, like you might say to someone, good, thank you for your crystal, but I'm going to science class, right? Like that's what this is like. Or the guy's like, he's just pointing you basically at a glass of beer and telling you that to be as drunk as he is. What I'm saying is, even the evidence itself is only counted as evidence once you call it evidence, once you think it's data. But when data is first data, it's data of a whole new kind. Like we were looking at points of light in the sky. Now someone's looking at points of light in a glass tube. Why do they count? You have to take a vote to find out if they even count or not as data. And this guy that's shoving your face in a tube and talking about the heavens is saying, therefore, you should now believe that your feet are traveling at 65,000 miles an hour all the time through the universe. Like one of you is asking the other to be dizzy and base it on what they're seeing in a tube. I mean, who's the crazy one? Am I making any, like, and I'm not saying, like, and Galileo's my hero. He is, but I think it's a very complicated story, and he's a hero of mine for very complicated reasons. Like basically why he's my hero is I'm pretty convinced that if I had been anybody at that time when Galileo was alive, okay, I might have even been smart. Maybe I was even rich or something, like maybe I was powerful. And if Galileo, and maybe I was even like a nice guy, I don't know, or maybe I was a priest, like I don't, but whatever, which could also be a very nice guy. But I mean, put me in whatever position you want. If Galileo invited me over to his house at that time, I'm pretty sure I would have been like, dude, get over yourself. I don't think, even if he showed me the evidence, is what I'm saying. If he showed me the evidence and said, like fresh off the presses, it would be so fresh. It would be like a vaccine to me today, honestly. And I mean, for whatever it's worth, like I took one, I'm scared shitless. Like, I don't believe it. I'm desperate. I'm afraid. I want us to go back to the world. So I got one, blah, blah. But I'm a scientist. That's why I'm afraid. I know those things didn't go through the trials that they're supposed to, right? And blah, blah, blah. So I'm saying back then, I don't mean that to scare anybody, but I'm just saying science is about skepticism. It's not about results. It's about a process of thinking. And the reason Galileo is crazy hero is because he's crazy hero. If I had been there to see exactly what he was showing me, I don't think I would have put that together and been like, yes, the floor is moving at 65,000 miles an hour. That makes a lot of sense. It doesn't. So Galileo would have to convince me. And here's what he would say. I'm just going to go for one more and then I'm going to pause. I'm going to just assume you get what but just so you see that I'm not just ranting. I mean, I am this is why I love physics. This is what I care about. But here's where it starts crystallizing into laws and stuff. Galileo has an answer. He does. I mean, he publishes it in various ways and he publishes it satirically. His answer to people who say, and what the question is the same as the train of thought question. The question is, why would you say that you're moving? Why would we say that Earth is moving? Why, how could we possibly, even if we have some reason to want to, how could we say it's moving if we have no evidence at all to suggest it's moving? And here's what Galileo said. Sorry. Okay, so I know we have 10 minutes. Because we have 10 minutes, what I'm going to do is, of course, I'm going to explain this and we are finally getting somewhere here. I'm going to try to explain this, but for the sake of everything, I want to give you two more forms first. I want to give you three forms at once before I explain any of them. So bear with. So the first form. This is one principle. This is and it comes in different writings of his, but it's how he answers the question, why if the Earth is moving could we not tell? How come we can't tell? How come there's no evidence of that? How can you say the train is moving if there's no evidence? Okay, so he has one answer, but it comes in it's said many different ways. And in a way, this whole class is about the different way. The truth of the matter is every next chapter of this class, every next topic of this class is just another way of saying this one principle. The truth of the matter is, once you say this one principle, if you really think about it, for the rest of your life, all of the chapters and all the equations and everything of physics comes out of this. Literally, it's all so everything that seems like a different chapter of physics or a different equation or a different formula is really a different form or a different wording of this one idea. And of course, the wordings get more and more complicated and sort of more mathy looking. But this is the central idea of physics, for real. I mean, through Einstein, and in fact, our belief that this is the central idea of physics does come from Einstein. So I'm saying from 1610 all the way through 1905 through now, this is still what it really means to do physics, is to believe this principle, but in all these different ways. So here's form number one. Again, I'm going to explain them, but if nothing else, even if I don't get to explain them fully, you'll have them from today. And this is the answer to the train question. And this is why we believe the earth is moving. So form, and this is how we do velocity from now on. But form number one is the laws of physics, whatever they are, hold, like are true, remain the same, hold fixed, enforced in all unaccelerated, so all constant velocity and reference frames. I have to explain more what a reference frame is. In short, I'm going to come out and say, hi, I'm going to come out and say, oh yeah, sorry, okay, sorry. Yeah.
The internet seems to be back down, but we can't connect this. Is there a quick button or something?
No, I don't think the internet is.
It's working for me. Totally working for me on my computer. Okay, I'll leave this.
Okay,
on.
yeah, let me, sorry. Reference frame is a big thing. We have to define in a big way, but in short, in quick, a reference frame is a perspective or a coordinate system. It really is a coordinate system, but a reference frame is we'll talk more about it, but the quick wording of this first form is that the laws of all physics, sorry, I'm very distracted. The laws of physics are the same at all constant velocities. I mean, you could put it that way if you want this first form, that as long as you are traveling at a constant velocity, the laws of physics will be enforced and will be the same as they are at all other constant velocities. Okay, that's the quick form number one. Before I get too involved in that, let me just give you another. Okay, and I hear we have 5 minutes. I know. Okay, form number two is, well, just what it says. It is impossible to design. It is impossible. Now, this is called Galileo's principle of relativity we're talking about here. Now, we're going to keep talking about this, but note, it's a principle. It's not a law of physics. This is coming before the laws of physics. I want you all to understand, like the laws of motion of physics that we do in this class, like Newton's the first law of motion, Newton's second law, and many of you have had it in high school or whatever. Obviously central to physics, Newton's laws of motion. You understand, this comes a generation before that. Those are the laws of physics. This is like the Constitution. This is the bedrock on which those laws are built, or from which those laws come. So this is an instruction manual of what the laws of physics must be in order for the whole world to make sense. Like before we even start doing physics, this is Galileo, like birthing physics, so to speak, classical physics, saying this is how the laws are going to have to work. First of all, whatever they are, they're going to hold true at any and all constant velocities. Like whatever speed you go, the laws will be the same as any other speed that anybody else goes. The laws of physics will hold at 80 miles an hour, 800 miles an hour, speed of sound, as long as you're going constant velocity. So therefore, second form says, so therefore, if you're sitting on that airplane, right, that we talked about, or a train of thought or a plane of thought or something, and you like wake up and you look at, you're like, are we moving or not? I can't tell. Or you're in an elevator or whatever. You look at, and you're like, oh, wait. And you look out and there's clouds or mountains or something going by. So you're like, oh, mountains are going by. Oh, I guess we're moving. But then you're like, not mountains, clouds go by. But then you're like, oh, wait, I don't know if I'm going past the clouds and the clouds are sitting still actually, or if I'm actually sitting still and the clouds are going past me, or some example like that. Like you go for a minute. Oh, I don't know which one is actually happening. I don't know if I'm actually sitting still or I'm actually the one moving. Well, form number one says either way, the laws of physics are going to be the same. The laws are going to be the same no matter which speed you're going, all speeds. So number two is now saying, if you want to find out if you're actually moving or not, you might want to do an experiment. You might want to do an experiment and do something like, oh, I know, I'll like drop something. Because I know if I drop something, I know, even if I don't know physics, I know from experience, if I drop something and I'm just standing in a parking lot, the thing I drop is going to land on the ground right below my head, right at my feet. That's where it'll land if I'm standing in a parking lot. So maybe I'll drop something, and then if it just like lands at my feet, I'll know I'm standing around, I'm not moving. But Galileo is saying, but guess what? That experiment will totally not work, because we just said that the laws of physics are the same whether you're standing or going 800 miles an hour. The laws of physics are the same at all constant velocities. And of course, they would have to be like, that's why they're laws. Laws don't change from circumstance to circumstance. So whether you were standing, whatever would happen in an experiment if you were standing still would be the same thing as what would happen if you were moving at 500 miles an hour, according to the first form of this law, of this principle. So the second form says, so guess what, dude? If you want to know whether it's the clouds moving past you or you moving past the clouds, if you want to know the trains moving past the white lights or actually the white lights are moving past the train, or you want to know whether the earth is actually sitting still while the sun goes past it, or the earth is moving while the sun actually sits still, you can't do an experiment. Not because the technology is not good enough. You'll never be able to do an experiment, never, ever be able to design or perform an experiment to figure out which is which, because no matter what, the experimental results will work out the same, because the laws can't change from one speed to another. So you can't do an experiment at all to figure out. Therefore, and this is where we're going to end. I know we're totally about to be done. And I know class was weird today, but this is the last thing we're going to say, and just keep going wherever you are on the homework. I know 4 people handed in the newest homework, which is amazing. But all just wherever you are is fine. But this is the last form. Says, okay, it's like 12:05. This is again, we'll pick up on this, but the very last thing I'm saying, and this is really what is meant by Galileo's relativity, is he's saying, look, first of all, form number one, I'm just saying, whatever the laws of physics are, whatever they are, I don't know what they are. I'm not making any claim. I'm just saying, whatever they are, they would have to be the same. Whatever the laws of motion are, they'd have to be the same laws at all different rates of motion, right? Otherwise, it wouldn't be a law, right? Whether you're going 5,000 miles an hour or 2 miles an hour, the laws have to be the same. But then that means whether you're going 2,000 miles an hour or 1 mile an hour, you cannot do an experiment to find out which one you're doing. All you could ever know is how fast you're going compared to something else. You could not do an experiment to find out if you were actually moving or actually still or actually going at any particular rate, because the laws of physics are the same at all rates. So all experimental results will be the same at all rates, no matter what the technology, and no matter what kind of experiment we haven't even thought of yet. Therefore, if we're going to be if we're going to be scientists, if physics is now, for the first time in history, going to be about actually data collected from the empirical world through our senses, rather than just idle speculation, or rather than just speculation, then we're going to say, since you could never, ever, ever get the velocity of a single object from experiment, you could only get how fast something is going compared to something else. That's all you could ever know from data. Then Galileo says, from now on in physics, that's the only meaningful way to discuss velocity. Velocity is meaningful only as a comparison, a relation between two objects. It literally has no meaning and no place in physics as just a description or a property of one object. There's no such thing as the velocity actual of an object. Earth does not have a velocity. Earth is going 65,000 miles an hour compared to the sun. It's going 0 miles an hour compared to itself. It's going 650,000 miles an hour past the galactic center. That's true. It's going 250,000 miles an hour past the moon. Like everything is just going at a certain speed. Every velocity is a relation between two objects. No velocity is a property of one object. That is actually the point of all the, but I'm going to go right now because actually everything is sort of falling apart in my background and I was trying to come in and I may have to cancel them. I'm sorry. I'm going to, if I've got to go actually, but I hope that was sort of something clear. Just stay with the homework. Goodbye, everybody. Bye. Sorry. Bye.